time. It feels like the most fundamental force in our universe. An arrow, constantly moving forward, pulling us along with it. 1 second flows into the next, creating the river we call our lives. We live inside it. We age because of it. We measure our entire existence by its steady, predictable march. And yet, modern physics tells us a deeply unsettling story. The flow of time might be an illusion. The solid, unchangeable river we perceive might actually bend, stretch, and slow down. It might not even exist in the way we've always believed. This is the great paradox of time, a mystery that goes to the very heart of reality itself. To unravel this paradox, we first need to understand what time even is. How do we measure it? In the past, humanity looked to the heavens, the rising and setting of the sun, the slow dance of the stars across the night sky. But today, our definition of time is far more precise. It's not found in the cosmos, but inside the atom. The international standard for 1 second is defined by the cesium-133 atom. It is exactly, and I mean exactly, 9,192,631,770 cycles of radiation emitted when a cesium atom transitions between two energy levels. This isn't just a convenient number, it's the fundamental heartbeat that synchronizes every atomic clock on the planet. From your GPS to the global financial markets, everything runs on this atomic pulse. In a very real sense, the time we measure is the vibration of matter itself. This definition gave us a solid, universal standard, or so we thought. Because in 1905, one man completely shattered our concept of universal time. His name was Albert Einstein. His theory of special relativity started with two deceptively simple ideas. First, the laws of physics are the same for all observers who are not accelerating. Second, the speed of light in a vacuum is constant for all observers, regardless of their own motion. The implications of these two principles were world-shattering. One of the most famous consequences is known as time dilation. It means that the faster you move through space, the slower you move through time. Imagine two perfectly synchronized, identical clocks. If one stays on Earth while the other is placed on a rocket traveling near the speed of light, when the rocket returns, its clock will show that less time has passed. The astronaut on board would have aged less than their twin on Earth. Time, Einstein proved, is not absolute, it's relative. My now is not necessarily your now. There is no single, universal clock ticking for everyone. For the first time, we saw a crack in the foundation of reality. The steady, reliable march of time was an illusion, dependent on how you were moving. This was just the beginning of Einstein's revolution, the first step in completely rewriting our understanding of space, gravity, and the very fabric of existence. Time was no longer a simple background metronome. It was a dynamic, flexible player in the cosmic drama. This realization set the stage for an even more profound discovery about the nature of time and its intimate connection with gravity. What if I told you that time travel to the future is not only possible, but it happens every single day? It's a consequence of one of the most brilliant ideas ever conceived, and it comes from a mind that reshaped our understanding of the universe, Albert Einstein. But before we get to time travel, we have to start with something a bit more familiar: speed. In 1905, Einstein published his theory of special relativity. It's built onto simple but earth-shattering ideas. First, the laws of physics are the same for everyone, no matter how fast you're moving, as long as your speed is constant. Second, the speed of light in a vacuum is the ultimate cosmic speed limit, constant for all observers. It doesn't matter if you're standing still or racing in a starship, you will always measure the speed of light to be exactly the same. This simple fact has profound implications. It means that our common-sense notions of space and time are wrong. They are not absolute and fixed. Instead, they are relative, flexible, and intertwined into a single fabric, spacetime. As you move faster through space, you actually move slower through time. This effect, called time dilation, is usually too small to notice in our everyday lives. But as you approach the speed of light, it becomes dramatic. This leads us to one of the most famous thought experiments in all of physics, the twin paradox. Imagine two identical twins. One, let's call her Stella, stays on Earth. Her brother, Alex, boards a spaceship and embarks on a journey to a distant star, traveling at nearly the speed of light. From Stella's perspective on Earth, Alex's clock is ticking much more slowly than hers. Years pass for her, while for Alex, on his high-speed journey, time flows at a crawl. When Alex finally turns around and returns to Earth, a mind-bending reunion awaits. Stella is now an old woman, while Alex has barely aged. He has effectively leapt into Earth's future. This isn't just a theoretical curiosity, it's a proven fact of our universe. We've confirmed it with incredibly precise atomic clocks. A clock flown on a jet plane ticks ever so slightly slower than one left on the ground. Astronauts aboard the International Space Station age a tiny fraction of a second less than we do. The effect is minuscule for them, but it's real. Time travel to the future is embedded in the very laws of physics, a direct consequence of Einstein's revolutionary equation. But Einstein wasn't finished. 10 years later, in 1915, he unveiled an even grander vision, the theory of general relativity. Special relativity dealt with constant motion, but what about acceleration? What about gravity? Einstein had a stunning revelation. He realized that the force of gravity, which we experience every moment, is not a force at all. It is the curvature of spacetime itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now, if you roll a marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. According to Einstein, this is exactly how gravity works. Massive objects like the sun and the earth don't pull on other objects with an invisible force. Instead, they warp the very fabric of spacetime around them. Planets orbit the sun not because they are being pulled, but because they are following the straightest possible path through the curved spacetime created by the sun. It's a cosmic dance choreographed by the geometry of the universe. This warping of spacetime doesn't just affect space, it also affects time. General relativity predicts that the stronger the gravity, the slower time flows. This is called gravitational time dilation. Time literally runs slower for you here on the surface of the Earth than it does for an astronaut in orbit, where gravity is slightly weaker. A clock at sea level will tick more slowly than a clock on top of a mountain. Again, this isn't science fiction. It's a measurable reality that has a huge impact on our daily lives. The Global Positioning System, or GPS, that your phone uses to navigate, relies on a network of satellites orbiting Earth. These satellites have extremely accurate atomic clocks, but because they are in a weaker gravitational field and moving at high speeds, their clocks run faster than clocks on the ground. If engineers didn't account for these relativistic effects both from special and general relativity, your GPS would be off by several kilometers every single day. The next time you use your Maps app, you can thank Albert Einstein. His abstract theories about the nature of reality are what keep you from getting lost. The effects of gravitational time dilation become truly extreme near objects with immense gravity, like black holes. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape. As you approach a black hole's event horizon, the point of no return, the curvature of spacetime becomes incredibly intense. For a distant observer watching you fall in, your time would appear to slow down dramatically. They would see you seem to freeze in time at the edge of the horizon, fading away over an eternity. But from your perspective, time would feel normal. You'd pass through the event horizon in a finite amount of time, entering a region where all paths lead to the singularity at the center, and the known laws of physics break down. Near a black hole, time is stretched to its absolute limit. Just hours for you could mean billions of years passing for the rest of the universe. It's the ultimate form of time travel, a one-way ticket to the distant future of the cosmos. From the subtle slowing of a clock on a plane to the dramatic warping of time near a black hole, Einstein's theories of relativity have completely transformed our view of the universe. They revealed that space and time are not a static background for the events of our lives, but a dynamic, malleable stage that is shaped by matter and energy. Einstein showed us that the universe is far stranger and more wonderful than we ever imagined. The speed of light is absolute, but time itself is personal. Gravity is not a force, but the shape of the universe. These ideas, born from thought experiments and mathematical elegance, are not just abstract concepts. They are the operating principles of our cosmos, at work all around us, from the orbit of Mercury to the GPS in our pockets. Einstein's legacy is a universe where reality is relative, and the journey through spacetime is the greatest adventure of all. We've established that time can slow down, but what if it could do more? What if it could loop, or even go backward? This is where things get really weird, and we enter the realm of time paradoxes. The most famous of these is the grandfather paradox. Imagine you build a time machine, travel to the past, and prevent your grandfather from ever meeting your grandmother. If they never meet, your parent is never born, which means you are never born. But if you were never born, how could you have traveled back in time to stop them in the first place? It's a head-spinning contradiction. Physics doesn't have a single, clean answer for this. One popular idea, often seen in science fiction, is the many worlds theory. It suggests that every time you make a choice that changes the past, you create a new, branching timeline. So, in one timeline, your grandparents meet, and you exist. In the other, they don't, and a version of you is never born, but your original timeline remains untouched. Another possibility is that the past is fixed and unchangeable. No matter what you try to do, the universe would conspire to ensure the original outcome happens. Maybe your attempt to stop your grandfather from meeting your grandmother is the very event that causes them to meet. This is called a causal loop, or perhaps, the very nature of time itself prevents these paradoxes. Maybe you can travel to the past, but you can only observe, like a ghost, unable to interact with anything. The truth is, these paradoxes expose the huge gaps in our understanding. They show us that our simple, linear perception of time might be completely wrong. And this leads to an even more radical idea. What if time doesn't flow at all? Many physicists, including Einstein, have considered the possibility that the past, present, and future all exist simultaneously. Imagine a loaf of bread. Every slice of that loaf exists at the same time, even though you only experience one slice at a time. This concept is called the block universe. In this model, the entire history of the universe, from the Big Bang to its very end, is laid out as a single, four-dimensional block of spacetime. What we perceive as the flow of time is just our consciousness moving through this block, experiencing one slice after another. The past isn't gone, and the future already exists. It's all there, fixed. So, the feeling of now might just be a feature of human consciousness, not a fundamental property of the universe. Time, in this sense, could be an illusion, a very persistent, very convincing illusion that governs every moment of our lives, but an illusion nonetheless. So, where does that leave us? We've seen that time is defined by the ticking of atomic clocks. We've seen it bent by gravity and broken by motion near the speed of light. Einstein revealed that time isn't a constant, universal river but something flexible, relative, and deeply strange. The ultimate paradox isn't just that time travel creates contradictions. The ultimate paradox is that we live inside this strange phenomenon every single day. We are born in it, we live by it, and we measure our existence with it. Yet, the deeper we look into its fundamental nature, the less solid and more mysterious it becomes. We've only just begun to scratch the surface of these cosmic puzzles. If you are fascinated by the deepest mysteries of reality and want to explore more concepts that challenge everything you thought you knew, make sure you subscribe to the channel. Because time is only the beginning. Thanks for watching.